Alright, another DraftScience video presentation. So, no comments, which, well, good. The last video survived without a bunch of ragged crap. Again, anybody who can provide some sort of counter arguments that somehow, some kind of counter experiment, I guess, is the thing we're really looking for. Something to prove that I'm wrong, that what I'm saying isn't true. Would be nice, but otherwise, yeah, not interested. Alright, so this one's going to be a tougher argument. So this time I'm going to say Professor Lewin's full of shit. The last time using Professor Lewin's experiment as a defense against cranks. But this whole catching a bullet thing is, let's measure the bullet's impact. Not so easy. To think of a way to do it where you can conserve the momentum in the sense that you'll create a transfer of the energy that is in the direction of the momentum. I mean, you need to be in one direction to be able to catch it. Now, you could argue that experiments where you can convert all of the energy into heat, then you can just measure the heat. Maybe that's theoretically possible. I'm not too sure. But I mean, collecting every impact, every part of the impact is a transfer. And what you're looking for is transfers that are really consistent. Like, it all goes in one way and it all goes into the next object. And so the pressure moves consistently. It doesn't move in vectors that aren't in the direction, because we're only going to measure direction in one dimension. And if there's momentum moving in the other dimensions, we can't measure it with the device, because our device only measures movement in one dimension, subdimension, however we want to look at that. So it's just the idea of how to catch it and transfer the energy without it being transferred to things not going in the same direction. So I'm just saying that's sort of the trick of all of this stuff, of doing this measurement thing. Now, bullets are really interesting. Now we have the technology where we can take strobed pictures of a bullet with a ruler behind the bullet, and we can see exactly how far it travels in exactly how much time, and get a very exact measurement of its velocity. But these mechanisms are really poor, and there's a philosophy behind that, what they're saying, that has to be understood, and that's what I'm disagreeing with, is this philosophy underneath it that kind of shows that the kinetic energy formula is nonsense. It's just not giving you ever a rational number, and there's better ways to measure the transfers of energy, and better ways to detect when your energy is going in some other, where you've transferred it to something else. I mean, so I could use the example of a pool ball. In pool, sometimes you just want to make another ball go sideways. Now, logically, you can understand that if I move a ball, okay, and then I just want to touch another ball and try to get it to go perfectly sideways, well, perfectly sideways would be almost impossible, but that when that happens, it's a transfer of energy, right? I mean, if I did that, if I threw a cue ball and hit a whole bunch, 100 balls, just barely nicked them, you know that the cue ball is going to lose momentum, that it's not going to have the same speed when it gets to the second ball or the third ball or the fourth ball, that each one of those movements had to come out of the momentum of the cue ball. The cue ball doesn't have some magical capacity to make motion sideways, and it doesn't cost it anything. So of course it costs it something. It costs it in its forward motion. That's a loss of it's transferred the energy already. So now it can't transfer the forward motion because it's already transferred motion sideways, if you get me, in some direction that you're not going to be able to measure. It's got more energy, it's got some amount of energy that's going out than it's going forward. So if you can accept that simple logic, and again, this is just an argument about poor logic. You want to say it's bad physics? Okay. But all we have is as a faculty is logic, the ability to put all the facts together and make them make sense. And what I'm saying is this kinetic energy formula forces them to not make sense. All right, so I'll play the big statement, and then I'll say some more crap, and then I'll play other parts of the video. But right here, you can sort of get the smell that it just doesn't smell right.
It's very easy. It's 1/2 times the total mass, m plus m, times v prime squared, which you also know now. And so you will see then, perhaps to your surprise, that if you compare the two, that 99.94% of all available kinetic energy before the collision was destroyed and therefore was converted to heat. That happened, of course, the heat was produced in that block.
So he just said 99% of the energy of the bullet was converted to heat, yet we're going to measure the momentum.
More than 20 million people use Grammarly.
Annoying. I mean, really, professor, get a job or something. Come on.
I'm going to change to...
This is just horse shit. So, you know, he has some excuse. Oh, I signed a contract with a company or some other kind of bullshit. You know, they paid me a big pile of money. I mean, putting all these damn commercials on your science videos is tacky. I wish I could convey such messages. But he doesn't care. Because he now has a bigger TV. And his wife has more jewelry. You know, more of an insurance policy against the future, which isn't looking too bright. Well, it's looking very bright in a sense, if you're really cynical. Anyway, anyway, you know, these videos were made by MIT. I mean, you know, MIT should have kept ownership of them. But anyway, whatever. I'm sure he didn't pay MIT for rights to them. Or didn't pay them much. Anyway. Sorry. Tacky shit pisses me off. So 99% of the energy saying was lost. Now you can just know that when the bullet went in there, it couldn't have lost 99% of its momentum, because you're trying to use the movement to measure how much momentum the bullet has. So, and logically, what I'm trying to argue to you people is there's no way you could create something, especially like heat, you know, heat that's radiation going in all directions, and say you're conserving your momentum in the sense of conserving it in being able to measure it in one direction. You've just converted into momentum in 500. You've just tangentially hit a bunch of balls in different directions. And clearly you're not going to be able to measure your momentum in that direction, you know, that one. Because you've created a bunch of energy in other directions. So it's just, on its face, you're saying if you lost 99% of the energy of the bullet, you couldn't move that 4 pound or 5 pound or 6 pound or 10 pound hunk of metal. You couldn't have done the movement if you lost 99% of the energy, and the energy is the momentum. So that's where we're going to go. This is only their game, that they make you think that momentum isn't a real quantity. And they're just making you think that. So earlier in that video, he actually does say, hopefully we can hit that part, he actually does make the argument that, you know, jumping onto a scale is measuring your momentum. So he actually concedes the argument that, well, sure, we could measure your momentum in an actual quantity. You know, we could turn it into exactly a kinetic energy kind of energy number. You know, because we know that, yeah, if you just step on the scale, you're measuring your momentum. So, you know, I really should find that exact clip, because I should play that sometime for certain. But I'm just saying that they're conceding the point that they're just not doing it. Okay, he's not conceding that point. I just mean that anyone who argues that momentum isn't a real quantity, an absolute quantity, is bullshitting. They've just decided not to use it as a quantity because they have this preference for this other formula. And so this is again why this dualism is so obvious. You know, that they are really, you know, that it makes absolutely no sense to have these two definitions. And so the only way they can make it make sense is they have to force one of the definitions to be ambiguous, you know, not explicit, when it is explicit. All right, so that part I am going to attempt to argue. So as stated, I would argue, get rid of the reflection. Yeah, so that's much more pleasant, I think. Anyway, okay, so the theory is that if I take 100 grams, or 102 grams, actually, okay, 1/10 of a kilo, whatever, gram. Yeah, all right. So that's a certain amount of weight right now. So right there, it has, in a sense, a momentum, because it is actually being moved by gravity. But the key point is that that's a Newton. That weight is 1 Newton. Okay, so that's a Newton. And then if I drop it 1 meter, all right, the impact weight, yeah, so that's what we'll call it, the impact weight, the momentum, is 1 joule. Okay, so this equals a joule. So when I take 100 kilograms and I gave it the velocity of 1 meter of gravitational fall, that's supposed to be a joule. So what I have found is that the velocity of falling 1 meter, okay, is 4.4. So we know we can just multiply 4.4 times 0.1, okay, and you will get 0.44. All right, so a joule equals 0.44 momentums. So whenever you do a momentum number, whenever you get the number from momentum, you know that it's 0.44 of a joule. So whatever the momentum number comes out to, you can just sit there and go, okay, that's 0.44 of a joule, because I know what a joule is. And I would argue this is something like, okay, a pound. And you can sort of get that, I think, because this would be in kilograms. Half of a kilogram, it's a little less than half of a kilogram then, you know. So I'm just guessing though, okay? I'm not sure how much. So it's a stick of butter. If anybody wants to try, if anybody has a decent scale, just drop a stick of butter from 1 meter onto a scale and, you know, catch the maximum reading you get. And that'll tell you, okay, and we'll find out what a stick of butter hitting the ground, how much it weighs, because that's really telling you a joule. So, you know, all right, so that sort of makes sense in the sense that you usually get a momentum number that's like 20, and the kinetic energy number is some kind of, you know, much bigger number. But I just mean it does seem like something like it might be a half multiple, that you could multiply this by 4. I mean, you could do the division and you would find out that it's 40 joules or something when it says it's 20. So like 20 momentums, right? My momentum, my MV number, okay, MV number would be, say, a 20. We can just convert it and say that's like 45 joules. So now we have a joule number to compete with their joule number, okay? What the 1/2 MV squared gets, okay? Now we have some other number to compare to it to say this is the real number momentum says in joules. And so that's part of this whole kind of a fraud, is the fact that they never gave momentum. They now currently, I don't know what they did in the past, but clearly now, okay, now they revisioned physics with this new formula. They took the meat out of momentum by denying it the ability to be turned into a real quantity, like a pound. Okay, so if we did say this was a pound, then this would be 20 pounds. You know, if you get the momentum number, it's just telling you how many pounds does it weigh. How many pounds does it weigh? How many pounds moving in this direction? That's the momentum. How many pounds? And the great thing about converting it into pounds is that now you can convert it into shapes, because now you can say, well, if I have 1,000 pounds and I point my 1,000 pounds, okay, very pointy, then I can figure out how many pounds per square inch, right? So the more surface my pounds are hitting with, you can understand that it makes a great deal of difference whether the 1,000 pounds are over 1,000 square inches or whether it's over 1 square inch. because now, I have a tremendous amount of energy in one area, in one place. And so it all kind of fits if they give momentum a real quantity instead of what they're doing now, saying kilogram meters per second. Yeah, it's 5 kilogram meters per second. No, it's 5 something reals. Okay, it's a real number of real energy. Okay, and so this is part of. I'm just saying that you can sort of understand the cheat here, right? The way they have reduced the importance of momentum and increased the importance of the kinetic energy. And you can see that part of what's critical to doing that is to give momentum in coherent numbers, is to pretend it's not a real thing. It's not some kind of quantity. It's some sort of abstraction. It's not, it's not real stuff. It's kilogram meter per seconds. What is that? What's a kilogram meter per second? That doesn't tell you anything. But a joule does tell you something. A pound does tell you something. All right. Yeah, I think that's all I wanted to say about that. So it can be put into a real quantity. And if you do that, then, and you compare these numbers, then you'll sort of get the idea of how this squaring thing is just creating preposterous exaggerations in terms of amounts of energy. It just doesn't have anything to do with reality. All right. So the other point I'd make. Okay, so let's go back and start at the beginning. Not the beginning, because we'll have to rush. We'll piddle through some of this stuff, and we can certainly make sure the speed is it's high enough. They use a ballistic pendulum. Now, it doesn't go anything to what this thing is, but it's really just a piece of steel with probably clay in the side, and you shoot a bullet into it, and it captures some portion of the momentum, right? Because it's really hard to capture the momentum of something moving, 200 meters per second. So, or 300. And so this is one way in the past they did it. Now, like I said, in modern technology, they can do it much more exactly. But regardless, doesn't matter. This is the way they do it. And it's over time you figure out what kind of averages, in terms of how far off you are. Now, the experiment he's doing is conceding 15%. He could, his margin of error is 15%, which isn't, which is rather significant, 15% error. And I would argue it's because the whole thing is built out of generalizations. They're basically compensating. They have another formula just for this pendulum experiment, just for this ballistic pendulum. It's really just taking into account the fact that you're going to lose a certain amount of your momentum to the environment. The environment of putting a bullet into the clay. And so you're not going to keep. I probably should draw this. Yeah, probably should. Just so everybody's clear that what I'm saying is you can't have it both ways. And you can't not understand that you can't move clay and heat clay and do all of that stuff without it taking the momentum away. Using it, converting it into another direction. So you have a steel cylinder full of clay. Okay, it's full of clay, and you're going to shoot a bullet into it. And so what's going to happen is that the bullet's going to plow through it. And what's it doing as it's plowing? Well, it's certainly creating pressure waves. So as the clay, so say the first inch of clay, what's it going to do? Well, as you're pushing into it, it's going to expand a pressure wave in all directions, right? Now the wave is going to be stronger here, just like a light. It's going to shine strongest in the direction you want it to. So that's good. It's going to compress clay this way a lot more than it's going to compress clay in these other directions. And the good news is the steel is going to push back some of that. It's going to reflect some of the energy that goes up against the steel. It's going to bounce off, and it's still going the way, it's still retaining a portion of its vector in the right direction. So that's good. Okay, but the fact is that you are creating vibrations this way. So say if I had a ballistic, one of these, so this is on a pendulum. So the trick would be is just to put a bunch of steel balls on top of it, you know, on little rods. Just put a little rod with steel balls on top of the metal thing. And then you could actually see that some of your energy is actually expanding the steel. You know, you're pushing against it. You're creating pretty significant percussion waves, I guess you could call them, into the clay. And the clay is pushing against the steel. And so when the bullet went in, you would actually see these little steel balls pop. You know, they would vibrate, indicating, I am losing some momentum to this direction. Okay, you can't do that stuff. Now, even the heat part, right? So you can sort of get my point. When the bullet goes in, it's going to create little, you know, bursts of energy that are also going to hit the steel, and the steel is actually going to do that little bit of vibrating. And those vibrations are all an expense to the environment. They're all going into the environment, okay? And they're going, and you're not going to capture them. That's momentum lost. That's hitting a cue ball into another ball over here, you know, and you just glance it, and it goes off this way. You've lost momentum. You have slowed down. You can't keep going the same speed after you've shot some of your momentum that way. And the same is true for all these little bits of clay that go the wrong way. Okay, they're all losses of momentum. And clearly the steel moving into the environment is losses of momentum. The steel's vibrating, that's a loss of your momentum. It's pushing into the atmosphere. It's moving atoms. It's, you know, lots of energy disappearing from what you want to do, which is move this whole object a certain distance to measure your momentum. So it's like the bullet in the bowling ball. This is your bowling ball. Okay, this is your bullet, and you're trying to make this conversion. But there's no real good way to do it, you know, mechanically. Like I said, with photography, we can just take pictures right on a scale, and we can watch exactly how far the bullet goes in a certain amount of time. No problem. Okay, so this is the old-fashioned way, this is the modern way, and I don't think these two answers will meet. Okay, if they do it both ways, they're going to get a much better answer here than they're going to get here, because this is really sloppy. Now, there might be just a certain percentage of the energy. Maybe it's 20%, maybe it's 10%, that will be lost to these motions in the wrong direction. Okay, in directions that you can't measure. Okay, because now the momentum's been converted, you've lost it, and you've transferred it to some object not going the right way. And so that's a loss to your detector. Your detector can't see the energy that went the wrong way. Your detector can only see the energy that's going the right way. So most of the energy will go the right way, but you have to concede you've lost a lot. But nowhere near 99.98%. I mean, come on, that's ridiculous. So it just, like I said, and the only reason why the kinetic energy number was so preposterous is because of the v squared. Of course, bullets have very high kinetic energy, you know, because they're going fast and you're squaring their velocity. But no, that's not what it's about. So this basically is the bullet in the bowling ball. You won't get all of the momentum. You'll get some portion of it. I guess it's whatever, 70%, some number that you'll recover. And that's it. We'll pause here for a second. Alright, should be back. Better check to make sure. It appears that I'm back. Alright, so you could say that, yeah, something like 20%. Probably the faster the bullet goes, this number changes. Slow bullets more. So it probably varies between 20 and 30% of a loss of the momentum in the right direction. So not a great instrument for getting this, you know, for doing the transfer to measure the momentum, the energy of the bullet. Alright, so yeah, that's probably enough of that. I'm going to play some of his video and then move on. I mean, I don't want to get lost in a whole bunch of, you know, his abstractions and blah, blah, blah.
We have a pendulum. It's a very heavy object hanging here at the end. I call it the block. You see it here.
So he could call it the bowling ball. And we're basically going to try to do an experiment. We're going to convert the energy from the bullet and we're going to put it into the bowling ball. So we're going to do the Newton's cradle in a very bizarre way where we're going to shoot something very light and very fast at something very heavy and such, and see if we can convert the momentum. And the argument, again, the simple argument I'm making, you can't do that. Just like the clay thing. If I made the two balls out of clay and they hit each other, the momentum didn't disappear. I mean, nothing's going to go anywhere substantially. I say they will turn, they will twist, they'll do lots of things. You'll see some of the momentum in movement. But most of the momentum is going to be lost deforming the clay. There's going to be momentum going in all kinds of directions. And when two objects are going in opposite directions and they're tied by a string, the chemistry, it means that those two basically nullify each other. They can't reach their potential because they're pulling on the same substance. So, they can't do anything dramatic in terms of making the object move because it's two impulses inside the balloon. And so they just cancel each other out. But that's the only place you can make a cancellation, so to speak. And again, we know we can't cancel energy. So it has to all eventually be dissipated as heat and permanent misshaping. I mean, when you've changed the location of the atoms, you've used up energy. Yeah, you've consumed it by changing the positions of the material objects. You don't get to do that for free.
And this pendulum is length L. Ours is about 1 meter. I will give you the exact numbers later.
All right, well,
And we know that there was kinetic energy here. No gravitational potential energy. I can call this level.
All right, so let's understand. So he's basically doing a momentum theory, but he throws kinetic energy in just a little tiny bit. Okay, so it doesn't have much to do with it, but he does state it, but you can see that the form of the equation changes dramatically.
U equals 0. But right here, if this difference in height is h, then all the kinetic energy has been converted to...
All right, so now what he's talking about is it's a pendulum and it's going to swing. Now, you can't measure the part going up, okay? So it's a very heavy weight, and you're basically going to lift it with the bullet, technically. That's what a pendulum's doing. It's lifting things. That's the stopping energy. See, it would just keep moving if it wasn't for the stopping energy. And so you could do this with a slide, not a pendulum. So, you could just have the thing slide on a track, but a pendulum is more efficient in the sense it has less friction and all that kind of stuff. So you prefer to do it this way if you can. But the idea is it's going to lift the heavy weight just a little tiny bit, in the gravity. But the distance of the pendulum swings this way, the sideways distance is much bigger than the up distance. So it's much easier to measure how far you go when you go up that far than it is to measure how high you actually went, because that's only going to be a few millimeters. So, but there's lots of theoretical problems with this, because obviously when you put that much torque on a pendulum wire, the wire stretches. Okay, so there's lots of little things that just make it also imperfect. It's just not easy to capture the energy of a speeding bullet. It's just not that easy to catch one and say, oh yeah, it was exactly this much spring energy. Now, you could make a really long spring, I think, technically, right? If you took a very long spring, and you put a little pad on the front, a little catcher's mitt, and because as soon as the bullet hits, it would start compressing the spring, so it would take away the energy very slowly, little pieces at a time, and get it very efficiently all in one direction. So I think there are mechanical devices that would be better than this. But anyway, continuing.
Gravitational potential energy. So we apply the theorem, the work energy theorem, or you could say it's equally valid. You could say we apply the conservation of mechanical energy. And so this kinetic energy, which is 1/2 m plus m times v prime squared, is now converted exclusively to gravitational potential energy, which equals m plus m times g times that h. Right. And we lose our m plus n.
Right, so he's just said that the kinetic energy has to be related to the gravitational potential, so he's converted the kinetic energy formula. He's just thrown it out right there. Right there, he just threw it away. Okay, it's obviously because it's only mass and gravity now, because you're going to determine velocity and essential by height. So he didn't say height squared. Okay, so we know the kinetic energy formula is already he just said we're converting it into momentum. Okay, so I said kinetic energy, but I'm really going to follow the momentum.
So V prime would be the square root of 2gh, and so all you would have to measure h, and then you know V prime, and if you know V prime, you know the speed of the bullet. But life is not that simple. It's very difficult to measure h, and I can make you see that. Suppose this...
Okay, so that's the part I just explained, right? It's going to lift very small distance. It's going to go this way, the pendulum. So when the pendulum swings, right, it's going up a tiny bit. This is a tiny amount, and this is going to be a longer amount. So if you measure the longer amount, it's a lot easier, and they're proportional to each other. So we can skip by some of that.
2gh can now be replaced by approximately 2g times x squared divided by 2l.
Okay, so the x squared divided by 2l is the notional formula that they created just for ballistic pendulums, basically. It's just basically telling you this is an approximation to deal with the fact that you really are deforming the clay and you really are doing some things that are destroying your momentum. So we'll give you back the percentage of the momentum you're losing because of how hard it is to have friction with a bullet and do all this stuff you need to do to catch the energy. You can't catch it efficiently, so we need this factor that's essentially a spring constant you're throwing in there. You're throwing a factor in to compensate for the fact that your momentum reading isn't going to be right because you did lose a lot of it to directions you didn't want that you can't measure.
Which is g times x squared divided by l. And
so L is the distance of the pendulum. The x squared is blah, 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 blah. Is the number you're going to read in this direction. And the squared part just has to do with the fact that it's proportional to the height, in the sense that this number is going to be the squared version of the height number. So don't be confused. It doesn't mean the energy squared. It doesn't mean velocity squared.
So the velocity of the bullet, v, which is n plus m, divided by m.
So just to understand, the g is there just to tell you that you're going to move into gravity. You're going to convert the energy from kinetic energy, or momentum, into a position in gravity, a height in gravity.
I bring the m down there, times v prime, but v prime is now the square root of this, so I get an x here times the square root of g over l. And what you see now, that in a very clever way, by getting x in here, we can now do a quite accurate measurement of the speed of this bullet, because we can measure x with a fair accuracy. Maybe
okay, so 15%, which isn't that accurate.
An uncertainty of only 1 or 2 millimeters in x out of the 3.5 or 4 or 5 centimeters.
Right, so not that impressive. All right, so I don't know if we need any more of
200
this.
grams, 3.2 kilograms, with an uncertainty of about 2 grams.
So these are just the starting weight. So it's 3,200 kilograms, the mass. What is that converting to? That seems way too high. I mean, that seems like a lot. 3,200. It must be in grams. Oh, it's in grams. Okay, so you have to. That's 320. That's still too high. Oh, it's in grams. So grams are 1/1000th. So it's 3.2 kilograms. So it's 6 pounds. So it's like the bowling ball. This really is pretty close to, a good analogy. I mean, a bowling ball is what, 16 pounds for an adult, but.
So we have a 10% uncertainty in the mass.
No, we don't.
We have a 2% uncertainty.
No, we don't need it.
And we can make you see the pendulum right there very shortly. And it is very cleverly designed. When the pendulum starts to swing, it's going to move a small object.
So bullets and guns.
There you have it. I can turn this on again.
This is
at the
just
largest
pathetic.
extension when the pendulum swings back. Okay, when we fire bullets, it's always a little risky. I have here the bolt. Put the bolt in.
It's amazing they don't have a police officer to
right. Comes the bullet.
make sure no one goes crazy.
And I cock the gun. Everything done right, yes. So you can look there and then see the swing of this very massive block, and the bullet will get absorbed in that block.
Do it.
You ready for this?
Yes, get to it.
3, 2, 1, 0.
All right.
I would say 5.2 centimeters. seems to me
Right. Okay. So we get the basic idea, right? So the bullet goes into the clay, but it is causing a lot of vibrations. It is causing a lot of other things besides the movement you want. So that's another reason why it just isn't a very, it's a very imperfect way. But you can approximate those, that error. And, you know, over, especially if you do this a few times with some sort of real empirical good results from another experiment, and come up with some number that's generally close. But that's all this is. It's just generally close, and I'm just saying the theory is wrong, that you're actually measuring the momentum, because you did lose the momentum to capturing, you know, grabbing the bullet. If the bullet deforms, if either thing deforms, you know, if I misshape in the bullet, like if I have the bullet just hit a steel thing and just flatten, I can't get the momentum because I just used a bunch of energy to reshape the bullet. So everybody could understand that. The more the bullet deforms, the less it can do for going forward, because the bullet has accepted the momentum and made the momentum move its parts around. So if I'm moving pieces of the stuff around, I'm losing the energy in other directions then. That's just the fact of it. And just like heat. So scattering bits, shooting bits off in different directions, is the same as converting it into heat. It's a loss to your measurement. Your measurement, you can't measure it if it starts going in directions you're not measuring. I mean, that's a simple enough argument. Leave it there.
about right. So X observed is about 5.2 centimeters. And we know the uncertainty of the 15% already. So I have to calculate now the 4.7 times 10 to the third, 4.7 exponent third, multiply by, I go MKS of course, so that is 0.0.
So it's 4.7. You know, I think I just pointed out that it's 4.4. Okay. But the 0.7 would be giving you what you've lost. That would be the 20% or the 10% you've lost to, you know, deformation. Perhaps that would work out, actually.
5.2, and that is 244 meters per second.
Oh, the 4.7 was actually the weight. Okay, sorry. Don't get confused. Sorry.
The last time we had something very similar. So the speed of the bullet is about 244 meters per second. It's a little under the speed of sound, which is 340 meters per second. We came to the same conclusion last time. All right.
So I might say something here. So that's why somewhere in here he talks about the...
We have kinetic energy in the bullet before the bullet hit the block.
Okay, so he didn't even calculate the kinetic energy. He doesn't give us that number, but we know it's a preposterous number. And the kinetic energy in the device that moved, we know is 1,000 times lower, you know, or something. It's a much smaller number. So we know the kinetic energy is saying we didn't transfer the energy. that measurement was completely, you know, shit, you didn't catch any of the energy, you know. But the whole argument is no, that is the same amount of energy. The bullet has the energy of the bowling ball rolling at 1/2 meter per second is the same energy as the tiny little bullet moving very fast. And that's the logic. Momentum is giving you the right answer. The point is, if he just showed us what the numbers would be, we would see that the momentum of the bullet is the same as the momentum of the cylinder, minus what I would argue would be 20% of losses.
And you can calculate how much that is, because you know the speed now, and you know the mass. 1/2 mv squared. You can also calculate how much kinetic energy there is when this bullet is absorbed in here. That's very easy. That's 1/2 times the total mass, m plus m, times v prime squared, which you also know now. And
so those two numbers will look so different that you'll be like, what the hell? What are you talking about? I lost all the energy.
You will see then, perhaps to your surprise, that if you compare the two, that 99.94% of all available kinetic energy before the collision was destroyed and therefore was converted to heat. That happened, of course, the heat was produced in that.
So that they'll never do, right? Now, do you really believe there's that much heat in that device? Now, yeah, it's not that hot. Okay, so if they really put it in a tank of water and pulled all the heat out and figured out how much heat it had, no way would it add up to 99% of the bullet's kinetic or momentum. You didn't use up 99% of the momentum. Didn't happen.
Block. Now I'm going to change to the concept of impulse. It's not completely unrelated to what we just did. An impulse is giving someone a kick. That's what an impulse is.
Yeah, this is
Our
the part.
bullet gave an impulse to this block. It gave it a kick. Impulse.
So the whole point is, impulse is a silly way to say it. It transferred its momentum. It's always a transfer. You're transferring between the atoms. You're transferring between a group of atoms. You're transferring between its whole substance. And the transfer, to be a transfer you can measure, you're measuring something in one linear direction. The energy is in one linear direction. You want to measure how much of the same direction after the interaction. And that's the only part you can measure, is the stuff still in the same direction. But if you hit a bunch of cue balls tangentially, okay, then you have a bunch of energy going this way. You have a bunch of momentum you transfer to objects not going the way you're measuring. And therefore, you're not going to measure all the momentum the thing had because you've transferred it to other directions. And that's all you do. You just follow the momentum. Always give you the right answer.
Impulse is a vector, and it is defined as the integral of f dt during a certain amount of time, let's say from 0 to delta t. Now f equals ma.
So again, this whole playing with forces is as if the force is always incrementally provided to an object in the right little chunks or something. The whole point is that the bullet and the bowling ball give you a great example that one of them can apply the force. If the bowling ball is made out of steel, I can move it and then move it into another steel bowling ball, and it'll transfer all of its energy, every bit of it. Well, 99% of it, whatever. Huge percentage. But as soon as I make those balls bigger, right, what happens? If I make steel balls really big and make a Newton's cradle, what's going to happen? Well, now the energy is going to be so high that when it hits, it's going to start deforming the steel balls, and they're not going to do the kinetic ball thing anymore. They're going to do the move the steel around thing. They're going to do the hammer hitting the sword on the anvil thing. They're going to start misshaping the sword. They're going to misshape each other, and by misshaping each other, by moving the atoms to new locations, they're going to use up the momentum.
Which is also dp dt. We have seen this now several times.
Yeah, I like that this is going the right way, right? So force is ma, but it's also dt over dv or whatever. I mean, it's basically telling you, yes, well, acceleration is just another way of saying what really is your velocity. It really is mv.
The rate of change of momentum, and so I can substitute that in here. And
so again, you're putting momentum in, which has the velocity component in it, and you're just redundantly putting the mass in again, which doesn't do you much good. So it's really Vp, right? I mean, it's really dv over dt.
I find then the integral from 0 to delta t of dp dt.
Right. So like I said, you could just take the p and say, why would I want to put mass in again? I already had mass in there, so we'll just take that out and we'll put the velocity back in.
And that makes me move to the domain of momenta. So I have now simply the integral over dp from some initial momentum pi to some final momentum pf. And so that is simply...
The change in the momentum is really going to be based on the change in the velocity, because you're not changing the mass. Nothing's changing mass in these circumstances. You only change one of the variables, right, at a time. I mean, theoretically. So we know for this example, we're always going to be changing the velocity. So mass is a given. And so when he says dp, what's the significant part of dp? It's not the mass, it's the velocity. So it's just change in velocity over change in time. Acceleration is gone. Disappeared. Irrelevant. We're back to mv. We're just back to mv. mv.
Final momentum minus the initial momentum. So what an impulse does...
So there, he's made it quite clear, I didn't use any kinetic energy formula here, right? There's no kinetic energy formula. So he really is saying it's all about the momentum. The impulse is all about the momentum. It's not about some kinetic energy bullshit. It's about your momentum.
Changes the momentum. There's a force that acts on something for a short amount of time. Could be a little.
So let's just understand that. So when people say F equals ma means I have to use the kinetic energy formula, clearly that's not what he just did. He clearly used momentum. He clearly converted F equals ma into a momentum formula, clearly. Okay, no kinetic energy formula here at all. No squared velocities, none of that crap. So don't pretend F equals ma is directly derived into the kinetic energy formula. It's pretty clear it's directly derived into the momentum formula.
Longer, as you will see with rockets, and that gives it a change in momentum. If we have an object that we drop on the floor, so we have an object mass n, and we drop it on the floor.
This is the good part.
And we let it fall over a distance h. That is going to hit the floor with a certain speed. We know it's down, the velocity, and that equals the square root of 2gh.
Now, that I don't think that you need. Okay, so the square root of 2gh, no, you just calculate the momentum. You have a velocity that will be created times their mass, done. Okay, you don't need this square root of 2gh. All you need to be able to do is figure out the velocity. So he's using 2gh to figure out the velocity, but we know there's easier ways to do that. It's just going to be, well, it should be 4.4. Well, it depends on what mass he's using. I mean, if it's a kilogram, then it's going to be 4.4. And if it's a 100 grams, then it's going to be 0.44 or whatever I said it was. Yeah.
If this were a completely elastic collision, which depends, of course, on the quality of the object, and it depends on the quality of the...
So again, the elastic only means in these cases, have I transferred the energy to something else? Am I transferring it to some other direction? That's all elastic and inelastic really means, is am I transferring it efficiently from one object to the other? That's what it should mean. Or is it an inefficient transfer because of the fact that there's a bunch of little pieces inside the objects moving all over the place. I'm deforming something. And every one of those little deformations have to consume momentum. You can't hit the little ball into the corner, into the side pocket. Okay, you can't hit it into the side pocket without sacrificing some of your momentum.
Or maybe a super ball or marble would be almost completely elastic. Then the ball would bounce back with that same speed. And if that were indeed a completely elastic collision...
All right, so that's the part where it gets a little bit... There's a difference between compressing something. So when a basketball hits something, or a tennis ball, it's not doing any kind of elastic thing. It's doing an inelastic thing in the sense that the ball is absorbing the pressure by deforming. And it's not permanent deformation, right? So it's the point is that it's turned the energy into a potential, because unlike clay, it can bounce back. Clay doesn't bounce back. Clay doesn't reshape. It doesn't try to get back to its original shape. So this is a storage of the energy in the deformation of the tennis ball, and then the tennis ball reforms. So it's a whole new energy event. You converted the energy into deformation. That is, you lost it because it went in the wrong direction, in a sense. And now you're going to release that energy and create a new event. It's a new event from stored potential because the object has a spring to it. I mean, if I just run something into a spring, I can collect the energy. If I run into a steel rod, I just bend it and it doesn't bend back because it's not a spring. So bending something doesn't do you any good. But it's like just I can take the same chemicals a battery is made out of and just have them on the table. Well, they're not a battery. They're not in the right shape to store energy. Okay, so I'm just going to lose energy if I put my, electrodes in there and shove the electricity in. I'm just going to make stuff change color and do some weird shit, but I'm not going to store the energy.
Then you can see that the impulse that is given to the ball, as the ball hits the floor is giving an impulse to the ball, and that impulse equals 2mv.
So we know, again, when the rubber ball hits the floor, the impulse to the floor is being dramatically reduced by the reshaping of the ball. The ball is accepting the energy, not the floor. And then the ball is going to use that energy it stored to push itself back up. The floor is not going to have that much to do with it now. I mean, it's certainly going to be two different events. the first event hitting the floor is going to be kind of weak because half the energy is going to deform the ball. And then when the ball bounces back, then the floor gets the other half of the energy. So it's essentially turning the one event into two events. By deforming the ball, you have a second event. I think that's a better way to understand it.
The ball changes its momentum. It was first mv in this direction, and now it's mv in this direction, so the change is 2 mv. So an impulse is given to the ball. Now,
So I wouldn't bother with this 2 mv because I don't think it's true. I don't think you get twice the momentum. I don't think there's two momentums anywhere in this. So this impulse thing is basically doing a complete transfer, a whole cycle. And it's basically counting both sides, and that's not really appropriate. So it's not really telling you what the energy is. It's not its momentum. So the 2 mv isn't another word for momentum. It's another word. It's just a word for impulse. And it really doesn't mean anything because the impulse, in my opinion, is still just the one momentum you hit something with. You don't calculate both reactions.
Collision were completely inelastic, then the ball would just say, like a tomato, I throw a tomato on the floor, it goes, pfft, no speed anymore when it hits.
So that's a bad example, again, in my opinion, because I can take something exact opposite of tomato, a steel ball, or a lead ball, even better, right? And I can drop a lead ball, and I'll just deform the lead ball, okay, and so the energy will be absorbed. So if I make things really hard, and I give them enough velocity, they'll dent surfaces, and that'll absorb the energy because you reshaped metal, which isn't easy to do. You have to use a lot of energy to reshape metal. And that's really all this is about, is just whether you reshape the objects or you don't. If you're reshaping objects, you call it inelastic. If it's elastic, you're not reshaping. That's how I would do it. But there's just no point in getting into this. The words are so inexact in their definition that there's just no point. I mean, when you start comparing tomatoes to steel balls or lead balls, you start saying that a tomato is like a lead ball. Well, that's pushing it, in my opinion.
The ground, then of course the impulse would only be mv, because then it doesn't come back up. So the change in momentum is then smaller.
So we know the impulse was the same, whether it comes back up or doesn't come back up. We know the impulse is, you're just calling the act of something moving, hitting something else, the impulse, right? We know the impulse going in is always the same, and whether it comes back or not, we know those are by these other rules. So we know it's only a certain amount of energy that goes in. You can't say because it's elastic, I only have one impulse. And inelastic, I have a half impulse. I mean, there's no logic to this, that's all I'm saying. I think he gets to the part here about the weight, I hope.
We have here two balls that look alike. They have a mass of 0.1 kilogram. So m equals 0.1 kilogram. And I will drop them from a height of about 1.5 meters. And that gives them a speed when they hit the floor of about 5.5 meters per second.
All right, so that's the trick, right? So it's 1.5 meters. It'd be so much better if you just dropped them 1 meter, right? Because then we could do this simple joule thing. So 1 meter, I guess, would be 4.4, I guess.
And so the momentum change is 2 mv.
See, I mean, it's the right 100 kilograms. That's what we want, 0.1 kilogram. And so because he has a height of 1.5 meters, well, that just, takes all the fun out of it.
So the impulse equals 2 mv is about 1.1, and that would be kilograms.
So the impulse, just by his own definition already, we know the impulse is just the momentum. And all he's done is change it by putting a 2 in front of it. I mean, it's the momentum.
Meters per second. And that means that if the collision time is delta t seconds, that the average force acting upon this ball during the collision with the floor equals the impulse divided by delta t, because remember that was our definition of impulse. So if we know the impulse, we get a feeling for the average force. And for the ball that I will drop on the floor, we have done fast photography. I will show you some results of the fast photography with a different ball, but nevertheless, we did it with the ball that I will drop on the floor very shortly, which is this one. That impact time is only 2 milliseconds. It's hard to believe that in 2 milliseconds, the entire collision occurs. And so if you substitute in...
Yeah, it was more like 4, but whatever.
Here now, 2 milliseconds, then you get for the average force 550 newtons. Just imagine, this ball has a mass of 0.1 kilogram. The weight is 1 newton. And during the impact, it weighs 550 times more. What an incredible...
Okay, so I don't know exactly how he got that, because that seems a stretch in terms of weight. But in joules, Like I said, we can measure how many joules it has just by recognizing the conversion number, right? What was the conversion number? 4? No. I forgot already. That's really... All right, I got go to the trouble to put a number on it. Okay, so it's like a pound per... pound per momentum unit. Right, so I just do the momentum. So I just do the 0.1. I think I'll need to pause here again. All right, I'm back. Yeah, so there's a lot wrong with what he's saying here. Just the 0.1 kilogram. So these balls are really small. I don't know if they actually do weigh 100 grams, but whatever. We'll see.
The acceleration that it experiences during the impact is 550 times g.
Right, so I would say that that number would have been 1/2 of a pound. So, I mean, if you did the momentum number, you come up with 1/2 pound. So the ball's hit with a 1/2 pound worth of energy.
People play tennis, and they have speeds of hundreds of miles per hour. Speeds are way higher than we have here, 10 times higher. And so the weight increase is even more. Now, if the collision were completely inelastic, so that if it would...
So again, the weight increase, so he's getting to it, right? The weight increase. So he's talking about, he's basically converting momentum into weight. And if they did that, then we'd all understand how momentum is a real quantity. It's not some kind of uncertain amount. It's an explicit amount. So then once they do that, then you can understand when you have these two different numbers. You know, you just convert the weight into joules. Then you'll get two numbers. Momentum says 50 joules. Kinetic energy says 150 joules. Then you'll understand that the two formulas are completely incompatible. They're making assertions about what it has. You know, how much it weighs. It's a real quantity, and they get two entirely different numbers.
For a tomato or an egg, and this one wouldn't come up, the average force would still be approximately the same. The reason being that the impulse will be half. But if the impact time were also half, and the impulse were half, then of course the average force will be the same.
All right, so he's just talking, that number is really the exaggerated number of the momentum being counted twice. So it's 225 newtons, and maybe that somehow will convert into a 1/2 pound. Yeah. A pound, right? I said a pound, right? Didn't I? A joule is a pound, right? Yeah. Okay. So this would be 0.5 joules. I mean 0.5 momentums. And that would be... Well, okay, forget it. I hate, well, whatever. I did it earlier.
Very high, but for a shorter amount of time. So I first want to show you now these two balls. One is almost complete elastic collision with the floor. Whether this is a complete elastic collision depends not only on this ball, whether this is a super ball, but also this one. Watch it.
So he's just
weight is about 550 times their normal weight. I'd like to show you fast photography on not this very same ball, but on another one that we has marks in centimeters.
Take 15 minutes to do this.
I'm going to turn 5 of these off. So there's a ruler in centimeters.
Ball falls.
This is 1 centimeter. I'll rewind a little.
Because
we're a little too late. Okay, we'll start again. So watch when it passes this mark. 1, 2, 3. You see 4 milliseconds for about 1 centimeter. So that's 2.5 meters per second. And now we'll count the number of milliseconds at impact. 1, 2, 3, 4, 5, 6, and it's off. About 6, maybe 7 milliseconds.
Yeah, so you said 2 before, right? So 6 isn't 2, but whatever.
There's no special ball. These impact times are amazingly short.
I think he's going to go, I throw tomatoes at you thing here now. I think. Come on, do the tomato thing. I was going to do the basketball thing.
Now I have something very special for you.
We'll skip
something
that.
Really special.
Because it's not.
Something like that. Who is in favor of higher?
Okay, so the tennis ball bounces way higher, than the basketball, because obviously they're both compressing into each other. All the energy from the basketball is going to end up being put right into the tennis ball. Obviously the basketball is much more massive, so all of its momentum goes into the tennis ball just because they're compressing into each other, creating they're turning the kinetic energy into potential and then releasing the potential in just one object. One object gets all the potential.
If this ball has a way higher mass than this one, of course the mass ratio comes into it, hit the floor, and it's not that I'm not only going to throw one tomato on the floor, but I'm very angry today. I'm going to throw a lot of these tomatoes on the floor.
Okay, there, this is the part.
N, as in Nancy, tomatoes on the floor. If one tomato hits the floor, the change of momentum is mv, if n is the mass of the tomato. But I'm going to throw n on the floor, so the change of momentum is n, as in Nancy, times the mass of the tomato times v. And this is the number of kilograms per second of tomatoes that I throw on the floor. So this is a change of momentum. And so this equals delta p divided by delta t. And that's an average force.
And it's only a pounds before it hits the ground. So let's understand it's how much the tomatoes will weigh. And what the tomatoes are going to do is transfer some of that energy into the floor. But frankly, a lot of the energy is going to go to tomatoes splattering all over the place. So if I was to throw the tomatoes at something that could break, okay, like paper towels or something, a trampoline made out of paper towels, you can clearly understand if the tomatoes don't break, the paper towel tears. If the tomato breaks, the paper towel doesn't break, okay, and it doesn't tear because I didn't transfer the momentum to the paper towel. I deformed the tomato. I shot pieces all into the atmosphere, and that way I dispensed with my momentum. I lost my momentum breaking the tomato. And, it's like this whole egg crushing argument. You can't say that you shot a bullet into something and then lost 99% of its energy. No. If you're measuring its energy, you can't say you lost its energy. You can only measure the energy you recovered in the right direction. And if you made anything else happen, you lost the energy and you didn't measure it. I mean, it's just, like I said, I'm saying the fundamental theory is wrong.
So the floor will experience...
They actually think you can deform something and that it doesn't have to come out of your momentum. That's essentially what Professor Lewin was saying. We'll go back to the beginning with the bullet. He's basically saying I can deform something, and the deformation didn't cost me any momentum. Of course it did. Just like the train example. I cannot possibly crush the front of the train or bend the metal or do any of that stuff. Change the metal's configuration and then say I conserved in terms of transferred. You didn't transfer the energy because all of that energy was losses in the wrong direction. You can't heat anything. If the trains get hot, I can't say, oh, look, it's got the same momentum. No, it can't have the same momentum. It has to lose momentum. You can just sort of understand it with the bullet and the bowling ball example. Unless I make the bowling ball out of just the right stuff that minimizes how many pieces break off. When the bullet hits the bowling ball, it breaks off the enamel, breaks this. If I don't reduce the amount of shatter and all of that stuff, I'm not going to be able to transfer the energy to the bowling ball because I lost it making a rocket fly into space.
A force in down direction. Of course, that was also the case here. When the ball experienced a force up, which we calculated here, the floor experienced, of course, the same force in down direction. Action equals minus reaction, Newton's third law. So the floor experiences a force in down direction. And I can write it down in a somewhat more civilized form. F equals dn dt times the velocity, if the velocity of the tomatoes that hit the floor is constant. And we're going to apply this to rockets.
So again, we're back to the same thing. We're back to force equals mv.
Whereby the exhaust out of rockets has relative to the rocket a constant speed. And this is then the number of kilograms per second.
I mean, we obviously didn't have any change in the mass, right, over time. There was no change in the mass over time. So we know that's just m.
That I throw on the floor. This is very real. I can throw these tomatoes on a bathroom scale. And if I throw...
I mean, so you have it right there. You basically have him saying it's F equals mv. Right there. He showed it. Kilograms. He put kilograms. Did you see it? I mean, he's basically saying it's F equals mv. Right there. There it is.
Throw these tomatoes...
There's no other way to look at it, right? Change in mass over change in time. Well, we know the mass of the tomato will not change. And he just said kilograms right there. So we know this is mv.
On a bathroom scale. And if I threw 4 kilograms per second on a bathroom scale, and they hit the bathroom scale with 5 meters per second, you better believe it that you will see that the bathroom scale will reach an average force of about 20 newtons.
Okay, let's just play that over and over and over again, right? So he's basically conceding momentum is weight. He's saying it overtly. All I have to do is throw the tomatoes, throw anything on the scale. The scale will tell me how much momentum it is. Just did that.
Meters per second, you better believe it that you will see that the bathroom scale will reach an average force of about 20 newtons.
So it's telling you how much weight the tomatoes have. Now, he said average force. So obviously we want to throw all the tomatoes at once to weigh throwing 10 tomatoes. So yes, you can do one tomato and get an average. Just say, okay, all the rest of the tomatoes are going to be pretty much the same event. But either way you do it, I'm just saying the average doesn't mean anything. He's basically just saying whatever momentum I throw on a scale, it's measuring the momentum. The weight is the momentum. So all I have to do whenever there's a momentum number is say it's 1,000 pounds, it's 500 pounds. And now the only thing that's going to be significant is what's the shape of that 500 pounds when it interacts with something else. Is all of the energy in one location? How is it? So the two steel balls hitting each other, we know that then, okay, now we can say they have a momentum, a weight, and we know all of the weight is going to be hitting a tiny, tiny surface where they're going to exchange it. So we know we have a tremendous amount of weight at the point of impact. I mean, a pounds per square inch is huge.
4 times 5. If it weren't tomatoes, but if they were super balls which would bounce up, then the momentum change would be double, and so the bathroom scale would...
So again, it's not double. It's not double. You're not doubling anything. You're storing and then releasing. You're not doubling.
Indicate 40 newtons. So this is a real thing. It's a real force that you can record.
All right, so there you go. He just conceded momentum's a real force that you can record, except we're always going to write it as if it's not a real force, as if it's some sort of kilogram meters per second thing that isn't a real thing. It's real pounds, okay? It's real joules, it's real newtons. You can convert it into real things really easy, and they don't do it for one reason, and that's because if they did do it, you would see the obvious duality problem, where they say, the momentums, this one has more momentum and this one has less momentum, but this one has twice as much energy than this one. You would see that and say, that can't make any sense, because I know momentum is also pounds. I know I could turn your kinetic energy into pounds. I can turn the joules into pounds. All right, so then we're stuck with two numbers, and the numbers don't match. You're just saying, this one weighs 50 pounds and this one weighs 100 pounds. And then you're saying this one weighs 10 pounds and this one weighs 400 pounds. It's not that the numbers don't match. It's that they're frickin' opposite each other. The thing that was light is now heavy. Huh? I mean, the lighter thing is now the heavier thing. It's not like the numbers are just off in the sense that you're saying one's going left at 50 miles an hour and really it's going left at 20 miles an hour. No, it's exactly the opposite. You're saying this object is going right and this object's going left. I mean, it's an insane duality. All right, that's there. I think I made the argument that, again, he's correct to identify momentum as weight, and once you've done that, then you've quantified it, and it's a quantity now, just like kinetic energy. And now you can just compare these two numbers and say which one is more realistic, and which one do I know is practically true. That is, if I shoot the two different weighted bullets out of the same gun with the same charge, okay, I can understand that the two bullets are going to have the same momentum. And that means the same energy. Okay. Yeah, I done my job, I think. Yep. Yeah, I did. I think that's enough. Okay. Well, we'll let Professor Lewin look at us. And oh, he did a smiley face. Isn't that nice? Yeah, he's throwing tomatoes at people. And then he talks about the tomato dribbling off. Well, when you throw the tomato, it's going to shoot tomato in all kinds of directions. It's not going to just drip off. Okay, most of the tomato is going all kinds of places. All right, so he didn't even get that part accurate. All right, so this has been a DraftScience video presentation. and such.